Thank you. I'm going to aim this talk at business people who don't know much about the history of AI and are puzzled why some people say these large language models understand what they're saying, and other people say they're just pastiching text together. So hopefully by the end of this talk, you'll have a more accurate opinion on that. I'm going to start by describing a tiny bit of history, and then I'm going to address the question of whether chatbots really understand what they're saying. And once we've resolved that, I'm going to talk a little bit about the immediate threats of AI, and then at the end, the longer-term threat of AI when digital intelligence gets smarter than us. So back in the 1950s, there were two paradigms: the logic-inspired approach, which thought that intelligence was all about reasoning, and you should worry about learning later, and the biologically inspired approach, which thought that intelligence comes from a neural network which learns connection strengths. You should focus on learning and worry about reasoning later. In biology, reasoning comes very late. So an artificial neural network, the typical one, has multiple layers of neurons. It has weights on the connections, and you learn those weights, and the idea is now you can learn to do all sorts of complicated things by learning these weights. There's an obvious way to learn the weights, which everybody thinks of. People like Turing mentioned it, where you take one of the weights, you change it a little bit, you see if the thing works better. If it works better, you keep the change. If it works worse, you make the change in the opposite direction. That'll work. That'll work even if you don't know how the network works. It just takes a long time. If you've got 1 trillion weights, you need to do 1 trillion different experiments to change each weight once, and you need to change the weights many times. There's an algorithm called backpropagation. There's just an efficient way to do the same thing by making use of the fact that you know how the network works. So if you've got a network and you know how it works, you can do a forward pass, and then you can look at the error in the output of the network. If you're trying to say whether it's a cat or a dog, and it says 50-50, and it's actually a cat, you'd rather it said 51 cat and 49 dog. And so you ask, how do I change a weight so that happens? And what you'd like to do is figure out for all of the weights in the network, how changing them a little bit would help or hurt. And backpropagation can do that for you. So it achieves the same thing as the mutation method. It's just more efficient by a factor of the number of weights. If the number of weights is 1 trillion, that's a lot more efficient. So for many years, conventional AI people, they didn't think neural nets was AI. They thought that was some rubbish biology. They said that this stuff will never work. You'll never train a big net starting with random connections to do anything complicated. And it wasn't an unreasonable position. It was fairly hopeful that you could train a huge net with random connections, and just from structuring the data, it would learn to do good stuff. In 2012, the dam kind of broke. Lots of people had done other good stuff before then, but there was a particular application for identifying objects and images, and my students in Toronto did much better than the state of the art in computer vision. And all the people in computer vision switched. They were very honorable. They switched very quickly. They said, oh, we said it was rubbish, but it actually works, so that's what we'll do now. That doesn't happen very often in science. But what about language? So people in the symbolic AI community always hated neural nets, said, this will never work for language. It's hard to believe that now. But if you look on my webpage, you'll find a statement to that effect. And I couldn't resist it, so I took the statement from this symbolic AI person explaining how this would never work for language. And I got ChatGPT-4 to explain exactly why he was wrong. Linguists were also very skeptical. Chomsky, for example, thought language wasn't learned. If you look back on that, that's a completely loony position. Chomsky couldn't figure out how it was learned, so he thought it couldn't be learned. And Chomsky is still saying this stuff doesn't understand anything. That's where the position that it doesn't understand anything comes from. Okay. Chomsky focused mainly on syntax and didn't really have a theory of meaning. So let's talk a little bit about meaning. If you take a word and ask what does it mean, there's two very different theories that appear to be just incompatible. One theory is the structuralist theory that symbolic AI people believed in, which is the meaning of a word is contained in how it relates to other words. In your head, you have a whole bunch of propositions in some funny logical language, And this word co-occurs with other words in these propositions in various roles, and that's what defines its meaning. Then there's a completely different theory that comes from psychology in the 1930s. The meaning of a word is a whole bunch of features, semantic features. And words that have similar meanings have similar semantic features. Like lion and tiger probably have pretty similar semantic features. Those two theories appear to be just completely different theories. But you can actually make them work together. So in 1985, I made a tiny language model. I see it as the predecessor of these large language models. And what the tiny language model learned to do was, it learned to assign features to words. It started with random weights. It learned to assign features to words, and then took the features of the words in the context and made them interact to predict the features of the next word. And then from the features of the next word, it could predict what the next word probably was. And it was trained with backpropagation. So it had a feed-forward net that took the words in the context and tried to predict the next word, and learned to convert words into features and have features interact to get more features, and then have those features predict the next word. So that's basically the way these large language models work. But it was a very simple model. It had like 1,000 weights, and it was trained on 100 examples. It's hard to think back now, but machines now go about 1 billion times faster than the machine I did this on. This machine took 12.5 seconds to do a 12.5 microseconds to do a floating point multiply. Okay, now this model didn't store any text. Its knowledge was all in how to convert words into features and how features interact. So it was a different view of knowledge from what most conventional AI people had. They thought in your head you have propositions and you have rules for manipulating these propositions. This model just assigned features to words. It learned the right features. It had interactions between features, and all its knowledge was in that. It didn't store any propositions at all. If you wanted it to produce a proposition, it would predict one word at a time to give you a proposition. It was generative AI, right? It could generate sentences, but it didn't have any stored sentences. Okay. So that's a completely different view of what knowledge is like. Now, the large language models are basically descendants of this, well, I think of them as descendants of this model. They've got many more layers. Instead of having 1,000 weights, they've got 1 trillion weights. They've got much more complicated interactions between features. They don't just sort of excite each other. They do matching and keys and things. So it's more complicated interactions, but it's basically the same kind of model. It's very hard to see what goes on inside it. In the little language model, it was easy to see what it learned. It learned sensible features, and so you could see it really did understand the domain it was trained on. Okay. So the idea that these language models just store a whole bunch of text they're trained on and pastiche things together, that idea is nonsense. GPT-4, for example, its first incarnation, didn't store any text at all. It just learned features and interactions between features, and if it wanted to say something, it would generate it. Another objection that comes from the symbolic AI people is, it's just autocomplete. You hear that occasionally. Well, old-fashioned autocomplete was easy to understand. You'd store little combinations of words, like fish and chips, and if you saw fish and, you'd look through and you'd say, hey, fish and chips occurred many times, so chips is a good bet. Fish and hunt occurred quite often, so hunt's not a bad bet. And that's how autocomplete worked. That's not at all how autocomplete works anymore. The big language models try and predict the next word using the features of the words in the context, using a multi-layer neural net. So it's not just autocomplete. And that kind of understanding, the ability to understand text by taking words, converting them into features, having features interact, and then having those features you derived predict the features of the next word, that is understanding. And people say, you know, these language models are totally different from us. The little language model I introduced in 1985 wasn't introduced as a technology for doing language. It was introduced as a theory of how people learn what words mean. So actually, the best model we have of how people understand language is these large language models. And the symbolic AI people will tell you they're nothing like us. We understand language a quite different way by using symbolic rules and so on. But they could never make it work. And it's very clear now that we understand language in much the same way as these large language models. Of course, there are many differences. They're trained on much more data than us, so they know a lot more than us. We can reason better. At least last time I checked, we could. That won't last that long. Okay. Another argument is hallucinations show they don't really understand. Well, people hallucinate all the time. So here's a good example. It's often, if you remember something from many years ago, it's very hard to know what the real truth was. There's a wonderful case that's been highly analyzed of John Dean's memory. He testified at Watergate, and he didn't know there were tapes. And he talked about all these meetings in the Oval Office. And these meetings never happened. They were confabulated meetings. But he was telling the truth. That is, given the meetings he'd been to, he was creating meetings that were very plausible, where people said the kinds of things they said in meetings to the other people who might well have been in that meeting. That's what memory is like, and that's what memory is like in us, okay? It's also what memory is like in these machines, and that's why they confabulate, and that's why we confabulate. So the conclusion so far is that these things are very like us. They understand the same way, they confabulate the same way. Now, once we've got there, we can now look at the risks. So there's a whole bunch of short-term risks, which is not my main focus of interest. There's false images and videos being used in elections. There's massive job losses, which some people think they won't happen. I think they will happen. There's lethal autonomous weapons. We'll come to those. There's cybercrime and deliberate pandemics, which are very scary. And there's discrimination and bias, which we won't talk much about because I'm an old white male. Fake images are clearly going to be used to corrupt elections. I think we should actually try and inoculate the American public. I've been trying to persuade billionaires to produce deliberate fake videos, and at the end of the video say this was fake. Trump never said that. That wasn't even Trump. I haven't persuaded them yet. But I think the American public needs to be inoculated against these things. And the way you do that is by having an attenuated version of the virus. And you do that by having a fake video and at the end saying, this is fake. Okay. It's not going to happen in the US because one party in the US is committed to perpetrating what they all know. Well, maybe not Marjorie Taylor Greene, but everybody else knows it's a lie. Okay. There's going to be massive job losses, just as the Industrial Revolution. When we made machines stronger than us, physical strength wasn't much use anymore. Being strong to dig ditches wasn't a good job. Most intellectual work is going to be like that now. Being a paralegal is already a very dodgy position to have, and it's going to get worse. So I think that's going to lead to lots of job losses, and I think that's going to lead to a lot of political problems. I don't know what to do about it. There's lethal autonomous weapons, which are clearly coming very soon. If you look at all the regulations, if you look at the European regulations, for example, there's a little clause in the European regulations that says, none of these regulations apply to military uses of AI. Governments don't like regulating themselves. And all the defense departments that produce, or the countries that produce armaments, they would never sign on to something like that. I think what will happen is we'll see very nasty uses of autonomous lethal weapons, and then there's a chance that we might get Geneva Conventions. For chemical weapons, they actually work, the Geneva Conventions. They're not being used in the Ukraine. The cybercrime and deliberate pandemics, which are very scary. Phishing went up 1,200% last year because it no longer makes spelling mistakes or syntax errors because it's all done with AI. For these kinds of application, I think it's very bad to release the weights of the big models. If you ask, why doesn't everybody have nuclear weapons? It's because it's hard to get your hands on fissile material. The equivalent for these large models is the training runs that produce the weights. If you can keep those weights secret, then people who want to fine-tune it for cybercrime, they can't afford the hundreds of millions of dollars it costs to train the model. But if you make those weights public, like Facebook and others are doing, then they can fine-tune it to do what they like. And I just think that's crazy. I think open source code is fine, but open sourcing the results of these huge runs means that smaller players can make use of those results and can commit terrible cybercrimes and can design drugs, viruses that will cause pandemics. So that's my opinion on that. My good friend Jean Lequin has a completely different opinion. But you shouldn't confuse open sourcing code with opening the weights. When you open the weights, it's not like hundreds of volunteers look for errors in the weights. That's not how it works. Cybercriminals grab those weights and fine-tune it to be good at cybercrime. Okay, I just said that. And I'm not going to talk about that. There's a longer-term existential threat, and that's what I want to finish with. That is that these things might wipe us out. There's many ways that could happen if AI gets to be smarter than us. Now, what you have to understand in order to understand whether AI might get a lot smarter than us is how different systems share knowledge. So I'm going to talk about 3 radically different ways of sharing knowledge. There's the old-fashioned AI way that says you've got facts in your head, you express them as propositions in sentences, and you put them in somebody else's head. There's a completely different way, which is what actually happens with people, close to what happens with people, which is I say things, and if you trust me, you figure out how you would change the weights in your head using some algorithm, probably not backpropagation, so that you'd be likely to say the same thing. Or I do things and you figure out how to change so you'll be likely to do the same thing. That's a very different model from shipping a proposition from one head to another head. And then there's a third method. Oh, that method is called distillation, when you try and behave the same way as the other system. And it's used for example, taking a big AI model and getting its knowledge into a small AI model. The small AI model has different architecture, so you can't just copy weights across, but you get the small model to imitate the outputs of the big model, and then you can get the knowledge across that way. That's distillation. The final method is if you happen to have many different copies of exactly the same neural network, and you can only have that if you're digital, analog that won't work. But if you're digital, you can have many copies of exactly the same neural network running on different hardware. And even though they're on different hardware, they do exactly the same thing because it's digital. Then you can get one copy and show it one bit of the internet, get another copy and show it another bit of the internet, and you can average the gradients they get. And now both copies have benefited from what each copy learned. And if you have thousands of copies, then you can get thousands of times more knowledge into the system than if you just had one copy. You've got rid of the sort of data bottleneck because different copies are looking at different bits of data. If we could do that, it would be wonderful. Each person in this room could go off and do a course in a different subject. We could average the gradients, and then we'd all know what everybody learned. That's what these things can do. And that's why they're going to be so much better than us. Once they're better than us, it's not going to be hard for them to get control. Bad actors will use them, of course, but we'll want them to be agents. We'll give them the ability to create sub-goals. And there's a very obvious sub-goal. The obvious sub-goal is, if I get more control, I can achieve my goals better. And they'll realize that, they're not stupid, and we'll be sunk. That's one way. Another way is if evolution takes place. Suppose you have several different superintelligences. They all understand that if they can get more data centers, they can get smarter. If they start, if one of them just has a tiny little bit of a desire to be more of me and less of the other guy, then what's going to happen is, I'm going to run over by 5 seconds. What's going to happen is evolution will start taking place and we'll be left in the dust. So my conclusion is, digital computation requires a lot of energy, which is why it didn't evolve. But in the long run, if you've got the energy, it's a much better form of intelligence because it can share much better than we can between different copies of the same model. Biological computation is better for now, but I think it's inevitable that digital computation will get better than us. And I think we should think very hard about how we're going to stay in control. And there's a paper referred to there that has the reasoned opinions of a whole bunch of people about what the AI risks are. And basically, I agree with that paper. Okay.